This is a Lepton Technologies infrared photodetector for the near-infrared portion of the spectrum, specifically at 1550 nanometers. It's an upconversion platform, and it was designed specifically to compete with direct detection platforms such as indium gallium arsenide or InGaAs detectors. Lepton holds a patent on the production of upconversion detectors. This is the first commercially available detector on the market of the upconversion flavor. What you're looking at is the input fiber here where the 1550 nanometer light enters the device. It's coupled with the output of a pump laser, which is integrated here, and the combined beam passes through an upconversion section of the device. What exits that section of the device is a signal in the visible portion of the spectrum. There's some filtration here to get rid of unwanted components, and the detection in the visible portion of the spectrum is done here, in this case by a photomultiplier tube. This could also be a solid-state detector, silicon in the visible portion of the spectrum. All of the electronics to support this device are here on this small PCB. Its interface with the outside world is here, and the output of the detector is here. You can see the quarter there for the size reference of the integration. This is a Generation 1 device which did not use a domestic upconversion medium. The Generation 2 device was able to source a domestic upconversion medium. We'll be seeing one of the Generation 2 devices shortly. It's much larger. It hasn't been integrated to this level, but the performance is very similar to this device. This is Lepton's demonstration area. Here we have a Generation 2 Lepton device, much less integrated than the Generation 1 device, as well as a competitor's solid-state InGaAs detector. What we'll do during the demonstration is to compare the sensitivities of these two devices to very low light levels. We have a source laser which generates the 1550 nanometer signal coupled into a fiber. Both detectors are fiber-coupled detectors. The light from that fiber enters a geometry here, a free space geometry. It comes into a collimator here, and there's an air gap before a second collimator that gathers the light into another fiber for a presentation to one of the two detectors. The geometry here is appropriate for, say, a pulse oximeter, where you might put your finger into the beam, or some other fleshy portion of your body. It's also appropriate for where the technology more developed, non-invasive glucose detection. We've also got some other supporting electronics here. This is an oscilloscope where we'll look at the electrical output of the two detectors when presented with the input light level. And we've got a counter, because the output signals are pulses, to demonstrate the signal-to-noise ratio that's achievable by the Lepton device at very low light levels. Let's take a little closer look at some of the equipment. This is the source laser. The 1550 nanometer signal is coupled into a fiber here, as well as an optical power meter. So we can, instead of coupling the fiber into one of the two detectors, put it into this slow power meter to get an idea of what sort of optical power we're presenting to the other two detectors. Right now, we're at a level of about 15 microwatts. That's 15 times 10 to the minus 6 watts, or about minus 5 dBm for folks that are more used to decibel type measurements. This is the oscilloscope that we'll use. What's being displayed right now is the output of the InGaAs detector when presented with the 15 microwatt input signal. The laser light is modulated on-off at a rate of about 10 kilohertz. The InGaAs detector has a lower bandwidth cutoff at around 1 kilohertz. The Lepton detector does not have that limitation, but we're not exploring that today, so we chose about a 10 kilohertz modulation to give a fair comparison between the two detectors. We're on a 20 millivolt per division scale right now. You also see here the counter that we'll use later on to demonstrate the signal-to-noise ratio for the Lepton detector. The next step of the demonstration will be to add a 25 dB inline attenuator to the optical signal to reduce the power level seen by the detector. We could have tried to look at the output of the Lepton detector at the 15 microwatt level, but that's actually too much light the detector would have saturated and we wouldn't have seen anything on the screen. But at the lower light level, we'll be able to see something. This 25 dB attenuator has been characterized here at Lepton. It's actually about 23 dB, which means that it will knock the power level of the light down by a factor of just about 100. So instead of 10 microwatts, we'll be looking at 0.1 microwatts or 100 nanowatts input to the detector. Now we don't see much on the oscilloscope, so let's change the scale. We'll go down to the most sensitive scale. This is now the 2 millivolt scale on the oscilloscope. Let's have a little closer look. What we see now at the 100 nanowatt input light level is really not a whole lot on the screen. If you squint, you might say there's a wiggle there between the on and the off state. To be benevolent, we could say that we've got maybe a 1.5 to 1 signal to noise ratio, where the noise is a measure of the width of this band here, which isn't very well defined. And we're on now a 2 millivolt scale. Okay? Let's bring the fiber to the Lepton detector and have a look at what we get then. The fiber has now been connected to the input of the Lepton detector here. I've moved the oscilloscope cable over to the output of the Lepton detector. And there's something on the oscilloscope, but let's zoom in a little more and see what it is we're looking at. The signal now is actually off screen. We'll change the scale of the oscilloscope. 1, 2, 3, 4, 5, 6, 7, 8, 9 scales to look at the display. Now we're on a 2 volt per division scale, as opposed to the 2 millivolt scale we were on with the solid state detector. Recall that the signal was barely visible on the 2 millivolt scale with the solid state detector. Now you can clearly see the signal, and the output, whereas before may have been 2 millivolts, we now have about 2 volts, a little more than that. So we're getting 1,000 times the output signal from 100 times less light level. The signal is clearly distinguishable as on and off. Let's look at the counter and see what the signal to noise ratio is for this signal. That is, when the signal is present versus when it's not present. How easily can we distinguish that? The counter will count the pulses coming from the detector, and if we take a count right now, we've got about 540,000 counts per second. Next we can turn off the signal laser, and let's take another count. These would be the noise counts coming from the detector, and we're at less than 5,000 counts per second. That's more than a 100 to 1 ratio, or 20 dB signal to noise ratio out of the Lepton detector, when the competing detector could barely even see the signal. Recall that the Generation 2 Lepton device is large because it uses commercially off-the-shelf components instead of an integrated arrangement of things. This is the pump laser. The input 1550 nanometer signal is coupled with that using a fiber coupler, which is on one of these layers. The upconversion section is here, and the photo detection is done here by, again, a photomultiplier tube. The electronics are on multiple layers because, again, they're COTS units. But this device could be integrated just as small as the Generation 1 device, which would be very comparable to the competing detector. That's it for today's demonstration. We'll be posting more videos soon.